Now, sorry, we're running a little bit late already. That's my fault. I apologise. So, we talked this afternoon, and first up, we've got an interesting talk from industry again. This is Robert White from Elekta. Elekta, who's going to talk about commercial control systems for commercial linacs.
Okay, thanks Dan. Thanks for that introduction. Good afternoon, everybody. Delighted to be at Daresbury this afternoon to tell you just one small thing about control systems. It's a huge topic, so I'm just going to pick one case story to present to you this afternoon. Before I do that, I must admit I was a bit perturbed by giving this slot straight after lunch by Dan. Thanks for that, Dan. You know, I think there's a risk that you're going to be asleep. So what I did, I've got out my beginner's guide to presenting, and it said, right, you need to either play some loud music to the audience, or you need to insist that you all go outside for a brisk walk in the fresh, cold air. I'm not going to be that mean to you, be pleased to hear, but perhaps you might want to just spend a few seconds taking in some fresh sea air, walking along this beach for a few seconds. Please wake up or go to sleep if you like. I really don't mind. So here we go. Right, so let's get going. So hopefully many of you will remember this slide from my colleague Per's talk last year, where Per talked to you about the application of accelerators that we're involved with at Elekta, which is for radiotherapy, for treating patients with cancer. The slide shows a number of the products that are on the market today, and there's around 11,000 accelerators in use at the moment treating patients. They're using ionizing radiation in the range up to 25 MeV, so really quite low compared with some of the big toys we've heard about this morning. So really fairly low energy in many aspects. And the kind of wave accelerating structures they are employing, typically tens of centimeters, perhaps up to a couple of meters again, so way shorter and smaller than the hundreds of meters that we've been talking about earlier. Now, I was very interested to see on the slide that John Walmsley presented earlier, ease of operation, because that's really the theme of my talk, and he didn't even know it, which is really good. So with 11,000 medical linear accelerators in the field, that takes an awful lot of skilled users. So all of these users, they need to be trained. And how on earth do you go about doing that? Well, typically there are three ways used, and the Michelin Institute is one of Canada's premier training institutes, and they use a combination of computer-based training in a classroom. Ideally, what they like to do was to use a hospital, where, of course, you've got a real medical accelerator, and so the fidelity is optimum. But, of course, by doing that, it takes the accelerator of clinical use, so hence you can't treat patients. And so perhaps a combination of the two techniques is the third one shown there, which is the use of virtual reality. And there I was trying it out a few years ago at the Michelin Institute. So, based on that approach to train these operators of these accelerators, the Michelin Institute approached Elekta and said, Elekta, what can you do to help? You know, how can we train our operators of our accelerators even better? What Elekta did was put our thinking caps on and think, right, well, what is it that we could create for you, Michelin Institute? What we need in terms of high fidelity of training is ideally a real linear accelerator. Problem with that is they can be quite hazardous, and so I thought, well, perhaps a real linac that doesn't actually radiate would be quite a good thing. The next thing we want from a manufacturing perspective is that we want to be able to produce a training accelerator which is virtually identical to the several hundred accelerators we're producing every year in our factory. So we really wanted to use our normal manufacturing processes. Once we've produced it, we need to be able to install the thing. And again, we're installing hundreds of these things per year. We've got people that can virtually do this with their eyes shut. And so we had to make the training system as standard as we could. So that meant that really the level of customization that we could apply was minimal. There are some other needs as well, and I won't list all of them. Cost of goods was an important one for a commercial organization like Elekta. By committing to a real accelerator, we've potentially got all of the cost of the components. But by having an accelerator that doesn't actually radiate, then there's the potential to make huge savings on the hundreds of tons of shielded bunker that might be needed. Safety, of course, is important as well. We can't really have a real accelerator in a facility that isn't shielded. So the approach that we chose there was to disable some of the high power components. And then this diagram, so this shows the completed proposal, if you like, or the concept that we put to the Mishra Institute, which is say a near complete, fully functional medical accelerator system, complete with low energy kilovoltage imaging, which is used for the current image guided radiotherapy techniques that they need to train their students on. And yep, the Mishra Institute said, Elekta, we love it, let's have 2, please. So off we went. Well, it was a good job. We managed to save them the hundreds of tons of shielding, because this slide shows the fact that the 2 training Linacs were actually mounted on the 9th floor of a building in downtown Toronto, whereas most accelerators I'm familiar with are always in the bunker of the building or hospital, and that's certainly the case with some of the things I know that you guys work on. So the saving of around 1,000 tons of material was absolutely essential if this project was to literally get off the ground, if you excuse the pun. So the next challenge for us is the technical one, and now we start to get onto the meat, if you like, of the presentation, is how do we make a real medical accelerator kind of work, but without working? The accelerator is fitted with a number of control systems that are involved in making sure that the radiation it produces is of the right energy, the quality of the radiation is good, the right dose is delivered, all under various fault conditions. Safety is always a key thing for the medical accelerator. So all of these control systems have been developed over the years and have all kinds of situations that need to be satisfied in order for them to work correctly. And the solution we adopted is this. The thing we called a dose emulator is basically a device that will fool all of those control systems on that accelerator into thinking they are working in their normal way. So let's break down the kind of functionality of what it needs to do. Perhaps goes without saying that it needs to certainly fool the dosimetry system. And in fact, there are 2 dosimetry systems that need to be satisfied. And the RF system needs to be satisfied as well. There's an automatic frequency control present, so that needs to be satisfied. And then the other key things are about beam transport, in terms of producing a beam, or simulating a beam, if you like, that goes up the waveguide, along the waveguide, and hits the target in the right place, and then produces a uniform flat beam of the correct energy. So that was the job of the dose emulator, and that was the customization, if you like, the custom additional control system that we had to create in order to fool all of those other control systems. So what's it actually doing? I've alluded to that already. So on Elekta Linacs, we're using a magnetron for our source of RF. So the key control system there that we have to satisfy is the AFC. The AFC works by varying the position of a tuner within the magnetron, and the servo system works by controlling the current through that tuner, which then controls its position, and that then changes the frequency of the magnetron, the output of the magnetron rather, and so forth, the frequency of the RF that's injected into the waveguide. There is then a detection system, an RF detection system with a phase detector, and if we create signals that duplicate the kind of signals that we would normally get from the phase detection system and inject that into the AFC servo, then we will achieve an AFC lock, which is what we're after doing. Once the Linac control systems have achieved, or they've been given the perception they've achieved an AFC lock, what it will start to do is ramp up the current through the electron gun to increase the emission, and therefore start to inject electrons into the accelerating waveguide. What we can do next is detect the value of that current through the gun, simply measure it. When it exceeds a certain threshold, we can say, aha, we think we've got electrons in the waveguide now. Let's start producing the signals that we would achieve at the multi-chamber ion chamber at the far end of the linear accelerator, and produce the signals to fool those control systems that the beam is being appropriately steered down the waveguide. There's a number of focusing and steering servos that all need to be satisfied by that process. And then finally, the dual redundant dosimetry system needs to be satisfied. So we need to produce the right size of signal for each of those dosimetry measuring channels, if you like. And they are different, and they need to track each other quite closely in order to deliver what would be a normally terminated clinical treatment. And then the whole lot needs to be done up to 400 times a second. That's the pulse repetition frequency of the Elekta Linacs that we currently have. So quite straightforward, really. So how do we go about doing it? Well, this dose emulator system with the device, as I say, we had to produce, and we had a fairly short time frame for developing it. So it was essential that we adopted some good development practice. And what we identified early on in the project, that one of the key success criteria would be ease of integration of the dose emulator onto the host system. So if we could produce a dose emulator system that we'd fully tested on the bench, wheeled it along to the host Linac, connected up, if that was successful, then the project would be successful. So what we did was include as many diagnostic features in the dose emulator system as we could. LEDs, dip switches, that kind of thing. But probably the most useful thing was a self-emulation mode. So here we have an emulator with an emulation mode. Crazy, we were going around in circles. But that was essential, because what we could do with the dose emulator is sit it on the bench in a lab, flick into self-emulation mode. We could then input the signals, or it would generate the signals itself, representing what we would get from the Linac, and then it would produce the outputs that would go into fooling the control system, and then the control system of the dose emulator, we could then monitor how that was performing, and we achieved that by putting a diagnostic CAN port onto the dose emulator, and then every time there was a pulse of radiation, we could see what all the parameters are doing and make sure everything was working correctly. In terms of the technology of the dose emulator, naturally we chose to use the same kind of technology that we'd use in the actual control systems on the accelerator, because that's the kind of technology we're familiar with. So an Altera FPGA was used as the heart of the device, which made the development nice and simple, because there was a lot of modularity to the various emulation parts. We needed analog to digital converters, digital to analog converters. Those are all the kind of things the Linac is jam-packed with, so we've just put a few of those together. No particular fancy requirements for those. Nothing happens in much less than a microsecond on our Linac. RF excluded, of course, but provided we could sample things 1 million times per second and then make an adjustment to the output, then we knew it would work. So yeah, that's the FPGA. Something else that was important in terms of development was compliance. Not heard compliance talked about today so far at the event, but it's certainly the bane of my life at Elekta. There are just so many rules and regulations that we need to comply with these days to make sure that, quite rightly, our products are safe when they're treating patients. So even a training system that isn't actually going to treat patients, we've got requirements for on electrical safety, electromagnetic compatibility, those kind of things. So we came up with a strategy that was, again, optimized at achieving compliance with the least amount of work. For example, the plot there is probably radiated emissions plot that we took, or perhaps conducted emissions. And really what we're trying to do here is just prove to ourselves and the regulators that by adding this thing called a dose emulator to this already compliant product, we're not destroying the compliance of it. That was the strategy that we successfully adopted. So on this slide, I show the realization of the dose emulator. So on the right is the kind of single printed circuit board you can see with all of the electronics of the control system. And you can see at the top there sort of common chunks of components, and those represent each of the, if you like, arbitrary waveform generators that we use to create signals that we injected into the ion chamber input of the Linac control system. And there's other bits and pieces on there. On the left is the unit packaged in its enclosure, and that's it installed on the rotating gantry part of our medical accelerator. So how did it work? I guess, how successful was it in terms of emulating dose? Got some images here that show, first of all, a scope trace showing one of the dosimetry channels of a real system. What we did then is do some circuit design, use a PSPICE simulator to say, well, how's our circuit going to work? That's the middle graph. And then on the real system, when we fitted that to the real Linac, hey presto, we end up with the same graph pretty much was good enough, because all of the parameters on our accelerator are adjustable. It's a digital accelerator, if you like, so we're able to calibrate out any small differences. So certainly the differences that we attained there from the design intent through to the simulation to the actual performance, we knew that it was going to be able to be accepted by the host accelerator. So then we took it off to the Missioner Institute in Toronto, fitted it onto 2 training systems that they had there. And then let the trainers come and have a look at it and come and have a play with it. And they all found it quite interesting. One of the things for us from Elekta that was perhaps quite striking is the fact, because the clinical accelerator does not produce the high energy radiation, just the lower energy kilovoltage for imaging purposes, we're able to have a lead glass window between the control room and the training Linac, if you like. And that really did kind of help the students actually see what was going on. So they could sit at the user interface, the user console, which of course is the thing they're trying to learn, and they could actually see what was happening inside the room at the time. And that just made the whole training experience that much more hands-on. And on this slide, this is one of the comments we had from one of the trainers. It absolutely performed brilliantly as a training facility, which was fantastic. So how do we do when we got to the end of the project? We were delighted that we had some very, very pleased customers, but inevitably it was appropriate that we think, well, how would we do it again if given the opportunity? Did we really do everything that we set out? Certainly the system performed well, and I make that judgment based on the comment that I had from one of our in-house radiographers, who we let loose on the training system with the task of, how well does this emulated Linac, if you like, actually perform? And the response was, yeah, it works really well. One thing maybe is every time I deliver a beam, it's exactly the same. And, they don't really work like that in a real hospital. So, I guess in many ways it worked a little bit too well, but nonetheless we took that as a pass. And so we said, yeah, really was a success. So much of a success that we've since developed 2 further systems, or installed 2 further systems rather, into our facility in Crawley. And now they're an inherent part of our R&D test facilities, where we can do all kinds of imaging workflows with an emulated high energy radiation. And it allows us to do lots of software testing, again, without that huge infrastructure investment of the shielded bunker. Engineering-wise, if we were to do it again, then what we would probably look to do is use less real components, because we really recognise that effectively we're putting a lot of active parts on that training system that weren't doing their job, and clearly that represented a waste. But we chose to do that as a strategy, because every item that we took off would have required additional non-recurring engineering effort, and we had a very limited time to do that. So overall, the project was a great success. Not for anything I did. Yes, I was involved in it, but here's just a list of some of the people that are involved in this successful project. And I think that is my last slide. So hopefully I've kept to time, Dan, and not. So I don't know if there's time for questions.
Yes, thank you very much.
Okay, thank you.
So, any questions for Robert?
Oh, yeah.
Up the back there.
You touched on it before. You said, every time it worked exactly the same. And I was thinking, when it says one thing would be really useful is a way of emulating faults.
Mm-hmm.
So that the trainer could flick a switch to say something wasn't working, and then that would give you useful systems to generate your control systems to check that you deal with them, and for the people who encounter a fault can train them how to cope with it.
So the training for this system, the training was aimed at the clinical operator. So what their operating system is purely in clinical mode, where they're delivering, preconceived, if you like, prescribed treatments, and not for, if you like, the service user training. But the authenticity of the emulation was so good that, yes, you certainly could extend the system to that. So, for example, introducing a fault could be changing a parameter in the calibration database, and then that would have an effect on that system. That would be emulated, and you'd be able to see that. So although we can't do that through the console, if you like, it was feasible with the solution we produced.
Train airline pilots in simulators, and they'll take an engine out, so they can still land it.
It wasn't for those kind of. I know what you mean. Good point.
Okay. Any other
Graham,
questions? Graham?
Nothing too complicated, I hope.
No. I was just. Was this a one-off to go to Canada?
It was a two-off, yes.
So you have one in Elekta?
And we have a couple of systems in Elekta, yeah.
Would you mind if other people came and used it?
Not at all. Come and have a
I
play.
think we actually had a discussion the other day there with the Institute of Physics, and there was talking about a need of a training accelerator. We were thinking of building an accelerator, but this is easier.
Yeah. Yes, the price has just gone up.
Any other questions? No? Okay, well, thanks very much.
Thank you.